Now we want to put all these ideas together and talk about counting electrons. So we know that we can put all four quantum numbers together to give us kind of the address of an electron. Okay, there is shell at the highest level, N, then L gives us subshell, M sub L gives us orbital, and finally M sub S gives us electron. Okay, that's kind of the lowest level order. And so each electron has a unique set of all four quantum numbers. So N, L, and M sub L basically determine what orbital you're in once all three of those are locked in. Then M sub S has two possible values, +1/2, -1/2, which means each orbital can be maximally occupied by 2 electrons. Okay, so we have all these different places that electrons can go, all these different orbitals, and each one can only hold up to 2 electrons. Okay, so what that lets us do is kind of parse everything out, put all of these different relationships together. So each orbital can be occupied by 2 electrons. We know that shell N contains N subshells. That comes from the relationship of those quantum numbers. We also know that subshell L contains 2 L plus 1 orbitals. Again, that comes from the restrictions on the possible values of M sub L. And so we have these, we know that basically you have a certain number of subshells, a certain number of orbitals, and then a certain number of electrons in each orbital. So we can put that, and then we can see that there is N squared orbitals in shell N. Okay, and then each orbital can hold 2 electrons. So shell N can hold up to 2N squared electrons. So I do want to point out real quick some different language. So when we're talking about, say, orbitals and shells, right, things like that, there are N squared orbitals in shell N. You can think about these orbitals and shells and subshells, they're boxes. So they're places where electrons can go, and so they always exist, right? They're always there whether or not the electrons are in them. But when we start talking about actual electrons, you will note shell N can hold up to 2N squared electrons. So when we're talking about a maximum number of electrons, that's like a roof, right? Or a ceiling as to what the total number of electrons you can get in there. But you can have less than that, right? That's a maximum occupancy. Shells and subshells can be empty, or they can be less than fully occupied. All right, so let's put this together then. When I think about subshells and electrons, we can see that S L equals 0 has 1 orbital, and each orbital can hold 2 electrons. So when I have an S-type subshell, that can hold a maximum of 2 electrons. It doesn't matter what it is, because it's all just based on the L quantum number. So S always has 2 possible maximum electrons. P, that's L equals 1, always has 3 total orbitals. And that multiply that by 2, we get 6 total electrons. D is L equals 2. We get 5 total orbitals. And any type D, any D type subshell, giving us 10 total electrons. F with L equals 3 can have 7 orbitals and therefore 14 electrons. And you'll note these are always true of S. Doesn't matter if it's 1s, 2s, 3s, 4s, whatever, it's 2 electrons. For D, for D, it'd be if you're looking at a D type subshell, say 3D, 4D, 5D, it's always 10. It doesn't matter which one it is. That's 10 total possible electrons. Again, these subshells can have less than that. This is the maximum occupancy. And so you can kind of see this starts to balloon out because as you increase shells, right? Shell 1 only has 1 subshell. Shell 2 now has 2. 3 has 3, so on and so on. And as you get to these more subshells, they can hold more electrons. So you start out at 2, then it's 2, 6, then it's 2, 6, and 10. So there's just a lot of electrons that you can start to put in there. So that third shell can hold 3 squared times 2 electrons because you have 3 squared orbitals. There's just a lot of orbitals in there. They can start to hold more and more electrons as these shells get bigger and bigger. All right, so for each of the following statements, we want to look at how we would correctly fill in the blanks. So there are blank subshells in the N-4 shell. So, and if we want to go from shells to subshell, it's just a matter of what is the value of N. So in this case, N equals 4, there are 4 subshells. We would call those 4 subshells 4s, 4p, 4d, and 4f, but in this case, we just want to know how many we have. It's 4. The 2 The 2p subshell contains blank orbitals. Okay, so this is going to be based on it being p. It doesn't matter that it's 2p. As long as you have a p-type subshell, that's going to be 3 orbitals. If we look at the next one, the 4p subshell contains blank orbitals. Again, it's 4p. That's going to be 3 orbitals. It doesn't matter what type of orbital, what subshell it is. As long as it's p-type, it's going to contain exactly 3 orbitals. The n equals 3 shell can hold blank electrons. For this one, we want to take our n and square it. So 3 squared, that's 3 times 3, is 9. That would be our orbitals, total orbitals, multiplied by 2, 18 electrons. Okay. The 3d subshell can hold blank electrons. Just like for 2 and 3, the number of orbitals was based on the letter. The number of electrons is again based on the letter, because you just want to figure out the total number of orbitals and multiply by 2. So d-type can have 5 orbitals. 5 times 2 is 10 total electrons. And again, that's a maximum occupancy. It can hold up to 10 electrons. It can also have less than that. Okay, so we have all of these quantum numbers and they define these different states. So then what matters in terms of putting electrons into things? Okay, and so it ends up when you have these different states, these different quantum numbers, it ends up that when in a given subshell, all of your orbitals are degenerate. Okay, so when we say degenerate, what that means is has the same energy. So you'll note this is a plot of all the different orbitals versus energy, and you can see for say 2p, all of those orbitals, the 3 orbitals, the lines are right next to each other because they're all the same energy. You could put electrons into each of them and have the same energy. You will note that within a given shell though, 2s and 2p, they are not degenerate. 2s is a lower energy. And so if you have an atom with more than 1 electron, which is most atoms, the orbital energies depend on n and L, which is the principal and then the angular momentum quantum number. So really what it comes down to is the different subshells have different energies, but that's it. Well, you only need to look at subshells. Different orbitals within a subshell, all the same energy, which makes sense because different orbitals within a subshell just have different orientations. So it's like a dumbbell pointing in different directions, but it's all the same idea. That n and L, though, determine size and shape. That's really going to affect how those electrons interact with each other and the nucleus, and therefore the energy.